So let's get started. I hope you have a good weekend. And then we have a holiday. I guess people are probably having holiday mood already. So let's quickly get to business. Unfortunately, our class is not affected by any the holiday this week or next week. So we have a full set classes for these 2 weeks. So let's get started. So I would like to start by quickly recall we have done, and then I think we stopped somewhere in the middle binomial, which then we will continue the journey from there, and then probably we finish all the discrete cases, and then hopefully have some time to cut to continuous random variable. So just to quickly recall what we're doing for the random variable is simply we're assigning number to outcomes, and of course you can assign any numbers. And the number have to be meaningful if you want to do some calculation or want to go further, right? Because you can assign any number, but number usually some measurements or something is actually meaningful in your cases, right? Like reward and gamble. So support is the number you can assign, and it depends on what kind of number you assign. Say discrete number 1, 2, 3, 4, 5. Continuous is just decimal numbers, right? So the question is looking at, say, discrete, you assign head or tail by number of heads or tails, right? So this is the leading example we have, and then you have pros and cons twice. Then you have 4 outcomes, but you can only count number of head or number of tail. Then you only have 3. So it kind of simplify, but of course it also means that we have to care about the distribution, even if the original case is equally likely, but because of you have a number can be associated with different outcome, then even the left-hand side is equally likely, then the right-hand side is not. So we need to study the probability function, right? And also we talk about continuous because of decimal numbers, but we don't talk about that now. So the discrete, to remind you, the PMF, the probability function or probability mass function is you just give the number of the random variable, the values, and then you give you the probability, right? So just nothing new there, but just instead of taking about probability event, but probability a number value, right? Numeric value there. And the CDF is the give you the probability that the random variable equal to that number or less, right? So that is the idea. Just you basically graphically is you from P to F is stacking the P's up and get F, and unstack the F, you get the P. So that is something we taught intensively last class. And after that, we talk about expectation. Just to remind you, expectation is actually an average. It's a long run average. A mean is the idea of relative frequency, right? Suppose you have this experiment many times. Each time you use the random variable to convert the outcome to the numbers, and your bunch of numbers because of a lot of experiment outcomes, and then average of this number will give the expectation. This is the mean, right? Do remind you that expectation would only make sense if mean makes sense, right? So if your you map your random variable to ordinal data, then probably it's not very useful, right? So have to be something meaningful. Otherwise, you get something, but the middle by center doesn't mean a lot, right? And then we also learn about the expected expectation have a linear property, right? So you can divide and conquer, you can calculate part by part, right? Remember the example is you have A shares of stock X plus cash B, then you can do the A times return or the price per share plus the cash. So this is the idea. And we also learn the variance, right? Variance is exactly the same as what you think, right? If you run the experiment many times, you have many outcomes, each outcome convert to number by random variable, and then you calculate the variance of such series of observations, right? And just to recall what you learned, the variance in the first topic, variance means how different for the data different from the mean, right? So basically the variation from the mean, right? And that also cover this a constructive property of the variance, which is variance of A of x is A squared variance of x. And U plus a constant has no change, right? Just if you have a portfolio, have a stock with the cash, if we just the variance is the risk of measure with the risk of the stock, right? Because the cash has no variation. Okay? And lastly, we talk about the if you have more than one number can represent outcome, then you use a bivariate. Of course, you can imagine you can use more than 2, can be 3 or 4 and 5 and multivariate. So that is, in general cases, you can have as many numbers as you want, right? Of course, the math will be much more complicated, but this is the P. The thing we need is P of xy, because this will define us what do you mean by expectation of sum, right? Because sum of the two number will be equal to the expectation of the each individual, right? Expectation of sum is sum of the expectations, right? So the variance do remind you that the variance would have the same property only if they're independent. So variance sum is variance sum is sum of the variances only if they're independent, right? So this important case is turn on later you will see is important when we talk about simple random sample, because each one we collect is independent, so you can have this property. So that's why we use this one. So that's why even though we don't use it directly, but we use it very soon. Okay. Of course, we use the proof to say how the mean of Benoni convert to mean of binomial, but it will heavily used in the second half of our course, maybe 1 or 2 weeks later. So we learn this formula is good to tell us stock X has high return and high risk. Stock Y has low return, low risk, and then you see how different combination give you different combination of risk and return. So you can see tell yourself or tell your customer or tell your boss what kind of investment mix would be the appropriate one. Okay, and this is the part that when done independent, then with the covariance. This is out of the scope of a class, but you definitely see in the investment class, because investment class is basically talking about all the covariances, right? If there's no covariance, then basically the investment will be very simple, right? Because you just consider things one by one, right? Because we don't care about how they're related, right? So you can do divide and conquer, focus on one investment. But because of these covariances, you have to consider portfolio at the same time, right? So that's why there's a portfolio choice over there. It's not just single. But in our model, we just have, in our class, we don't have to worry about this part. Okay. So now, this is the last part we cover. Hopefully, we cover everything in this class if we're ambitious enough. So basically, we just cover 5 different important applications of what we learn. So basically, this is called probability modeling when you go to if you want to learn further, right? Because you have futures, you don't know what's going on, you have a past data or engineering knowledge, and then these 5 would be the commonly seen one that you can apply nicely in practice. But of course, you learn how we use this 5 common one. You can easily look at more, because it's easy to see how these things can be applied. So that's why this is an example. If you have more things to be done, then you can just look up the web, because there's so many. If you look at this distribution, you can have at least more than 100 of this kind of stuff. But we just focus on the first 5. That was the simplest one. So this is nothing important. You know where already, because if every outcome is equally likely, then every outcome 1 over n. And as I said last time, this is important as a starting point. If you don't know what happened, you don't know which outcome is more equal likely, and then you use the base rule to update it. You become another style until you get the one you start, right? You like and then stop, or experiment tell you that this is going to be the one that you're looking for. Then this is the one we use. Okay? But this is just for sake of illustration. You guys, the most useful one is what we call the Benoni, which is the foundation of what we're going to cover. Benoni is probably the first distribution ever being developed formally by mathematician, is looking at the world where you only have two outcomes, success or failure, right? It doesn't mean that the world only have two outcomes, but you disregard any unimportant part, just care about you success or you fail, right? So we don't really care about how much more than you get. Just like imagine you want to get a job, right? You just either you get a job or you don't. You don't really care about how the interview marks, right? Whether you get 99 or 100 or 98 doesn't really matter. As long as you're highest among all, then you win the game and then you are the winner, right? So the same. So here we have success and failure. Failure has probably 1 minus P, success at P. And because only two outcome and just do once with number of success is a 0, 1. Okay, and this is the X. The P function, the probability mass function, is just simply represented by this table. Of course, you can draw a chart. You can plot it. It's not a problem for you, I guess. And you have seen this chart already. And the important part is we learned the probability mass function. The P function will be like this form. And this looks pure mathematics, but you will see this is how you would do when you do binomial, right? Because this is no different from the table we have seen in the previous slide, right? This guy, same as this guy. There's nothing new from that one, just same as this guy, right? But the way you write it will be helpful when talk about the binomial distribution. And the mean is P, and the variance is P times 1 minus P. I already explained why it's the case, but I hope if you want, you can check the proof, because the proof is a field line there. Just direct calculation if you really want to know more. But I just need to know this formula, right? Because basically all the distribution, you want to look at the shape, how it looks like the shape, and what's the mean with the variance, what's the P, then this is the main thing you want to get. Of course, you actually, if sometime you want to get the skewness and kurtosis as well, but for our class, we just focus on mean and variance. You can also do interquartile range, median, those kind of stuff. But take for example, look at Wikipedia, they can show all this, that. But we're not interested in those for the moment, at least for our class. So the next thing we basically stop somewhere here is the binomial distribution. Let me stop, maybe slow down a little bit, because I think this is the very important thing. Binomial distribution is very useful. As later you will see, it's closely related to the bell curve. Okay? And many of time we are asking yes, no question, and that's binomial. Okay? You can imagine we're asking, say, why binomial is important, because very often this related to the binary data. You ask people whether they like, I don't know, whether like particular pop singer, right? I think I saw in last Saturday there's a drone thing that I think 17 from the Korea. Then I go to the one Chai, I saw there's a drone exhibition and the thing. But you ask people whether they like 17 or not, right? Then if you randomly draw a person, then the P and the 1 minus P with the proportion of people in the population, they like it, right? So that's why you ask yes, no question in survey. This is a binomial distribution, okay? Or you ask people who like particular brand, right? This is what you have that, right? Then the question is, what is binomial? Binomial is simply you ask 10 person whether they like particular product, right? They would like a brand, Korea pop star, right? That is for singers, right? Then this is the question, right? Because you randomly pick up person to interview, then each one is individual. And the probability that you think that he or she will answer they like the product will be a trial, right? So this is a very important one, because when you ask yes, no question, this very often that happens the case, right? And in very often you don't care about whether the first one is yes, second is no, right? You care about the how many people actually like it, right? So that is by number of success, or number of people who like a particular product or particular thing you were interested in, right? So it's yes, no question. And last class, we kind of explained why we have this probability, right? And let me go it again to try to convince you this is true, because I hope to make sure that everyone will have a good understanding what's going on there. Okay, so you can imagine we are now doing a probability tree here, right? Probability tree here. Okay, so you ask the first one. First one, say particularly they like a pop star I, right? We call the singer A, right? We ask singer A how people like it, right? In the population, maybe P fraction of people like it, okay? And 1 minus P people don't like it, right? So in that case, I better pick up one guy to ask, do you like A, right? Then someone say yes. Some people say no, but you would guess the probability say yes with P. 1 minus P would be no, right? So that would be the question. Or maybe I just write yes here, no, right? Maybe I just write count how many people like it. This is 1, this is 0, right? And this is the first one you ask. You ask the second one. Second one can also be yes or no, right? You pick up a random person, and the probability should be same as P1 minus P, right? Because you're independently drawing people from the audience, right? Then this becomes 2, this has become 1, right? Because why 2 is above? Because you like it, right? In total, there are 2 people who like singer A, right? Similarly speaking, if say yes and no, with the same probability P, 1 minus P here, that will be 1, this will be 0. All right, so this is the case of binomial if you have 2 trial, right? 1 trial and second trial. Okay. So let's see this table here, right? If you look at this, right? If you have x 0, 1, 2, what is P of x, right? P of 0 is simply this guy, right? This guy is simply what? 1 minus P squared. Why? Because you multiply this along the tree, right? And the next case is look at this 2, right? 2 what? Will be P squared. Why? You just multiply along the edges, right? And what about this guy? 1 will be this 2, right? So it will be this times this plus this times this, because you add together this addition rule, right? Because it's yes and no and yes, right? So it will be P1 minus P squared, right? Can you see that it's yes, no, and no, yes? So the 2 cases, okay? So now let's see why the formula we have is like this. Okay, the formula is 2 x px 1 minus p 2 minus x. So if you look at the formula, it'll be like this. Okay, I'm trying to convince you this formula is right. If you replace 2 by n with the general formula, right? Because the general formula, if you look at it, you have done no notes, it's like this, right? You still remember the formula. And the notes is nx px 1 minus p n minus x. So this is the binomial probability function. So let me explain a little bit why this is true. Okay, but I explain it by the 2 cases. So what would happen if you have 0? Suppose the simple case is, how can you have 0 if you only have 2 fails, right? Right, because all the fail and fail, right? So in order to fail is fail and fail, right? Fail and fail is fail and fail, and because independent, right? The multiplication rule is just multiply together. So 1 minus p times 1 minus p, okay? And that is fail and fail. So that's 1 minus 1. And how many different ways you can have fail and fail, right? That's one way, because there's 2C1. Why 2C1? Imagine that you have two balls here. You draw two balls here. Okay. If you draw a ball there, they're successful. Right? If you draw one, the first round is success, second round is fail. If you draw two, the second round is success, first one is not. If you draw 1, 2, both are successful. If you draw no balls, then it means that there will be none are successful. So what do you mean by 0 means you draw no balls. How many ways to draw no ball? 2C 0, right? Right. So it's 2C 0 there. Okay. So that's why we have that. And now go to the second one. Okay. Why this is 2C, this is 2 here, actually it's 2C1, right? 2C1. Why? So remember you have 1 means success and failure, right? You have 1 means only 1 success, right? 1 success or fail, okay? Then you have success and fail is P times 1 minus P, right? And how many ways you can do it is because there are 2 balls there, right? You can have 1 way is only 1 or only 2, right? So success the first time, success second time. So that's why 2C1. And the last one will be 2C2, right? And that's 1 way to pick both balls, right? So that's why 2C2. So in general, that's why this is the case. Okay, of course. As I said, this is already in the gray box. So if you get it, you get it. You don't get it, you memorize it, or you just write down in your cheat sheet when you go to the exam, right? Or look at it in the assignment, right? So that is not super important. I think I didn't get it until very end when I probably the first course of statistics. I don't understand why is the case. I just memorize. I think after I do second or third classes of statistics, I understand. I mean, it took me quite a while, but I hope many of you understand. Take an instant to understand, but it took me quite a while, long while to understand what's going on. But if you don't, it's okay because I didn't get it the first time. So that's the formula. If you don't, just remember this. This is what it is. Okay. So probably want to explain this NP and NP at 1 minus P. The very simple reason is because it's sum of independent Bernoulli, because sum of the mean, sum of the expectation, right, is expectation of sum, right, regardless independent or not, right? The variance are same idea, but because independent, just helpful, right? Because just sum of all the trial. So that's why this is the case. Okay. So that's why it's not n squared. You may ask, why is it not n squared? Some of you may ask, because some of you make a mistake. It's why not n squared? Because it's not multiplied by n. It's each one you have n different random variable. It's not a 1 variable times n. Okay, that's very important because some of you may think, why is not nx? It's not nx. It's x. Let's say n different variable add together. It's x1 times x2 times x3 of xn. It's not n of x. So you can see the difference, right? Because you can have first one success, first one fail, and second one fail, success, fail. You can have different realization. If you multiply n, means that you have only once, and either all success or fail. Okay, so that's very different idea. So it's not, there's no square because it's adding up n independent. Okay. Now I guess that's enough for the thing. We go to the example, which I think that is the very good application to see why it makes sense, because this is very important operation. An example like this is a restaurant, an owner who figure out from his data 30% of time of the customer like spicy food, right? So what's question he's facing is he want to see our 5 customer or 5 table, 2 of them like spicy food. Why you care about that? Because maybe he run out of spice in his restaurant, he need to buy it, or the spice have to be prepared in advance, something, right? Have to pre-process it. You can't wait until the customer come and do the process, right? So you have to do probability and see how many to prepare, right? You can't really just in time because it's not put the food in the microwave, you are done, right? You have to freshly prepare, right? So you have to figure that out, right? So that is very important. So how can you do that, right? So this is just simply a standard idea, right? Because you can imagine this following, right? Imagine that there's a 5 customers going to come in, right? And assuming they're independent, right? So the restaurant owner would think, okay, because historically, 30% they like spicy food, right? So that means that I pick a random customer here, okay? There will be 30% that like spicy food, right? And then 7% they don't like spicy food, right? So the question is, asking the question is, randomly chosen 5 customers, how many like spicy food, right? So I want this happen, right? So asking this question. Okay. If it's just this, right? The first one like it, second like it, the third and the fourth don't like. That's very simple, right? Because if just follow this only one order, then we just 0.3, 0.3, 0.7, 0.7, 0.7. You just multiply them. End of story. Nothing more, nothing less. But the problem is we don't care about the order, right? We care about actually 2%. So you have to multiply. You can swap back and forth. That means that you have 5C2. Why? Because just like your 5 number, 1, 2, 3, 4, 5. How many ways you can pick up 2 numbers there? You have 5 balls. You pick 2 balls. If you pick ball number 1, number 2, it's like this. If you pick ball number 2, number 3, will be just this guy swap to the other guy, right? And then how many ways you can do it? 5C2, right? So that's why you have this statement, right? So that's how you get the solution, right? Because if you don't care about order, just multiply, right? That is just because of independent, right? So probability of A and B and C and D and E, right? Just multiply together, right? Because it's independently realized. But because we don't care about the order, we need 5C2. Is that clear? Of course, you can immediately see this is a binomial, so you can just apply, right? If you don't want to do this kind of drawing thing, but because you see it's binomial, right? Because you have 5 trial, and each trial have success 0.3. That's the case. Okay. And of course, this may not be something that the restaurant care directly, right? Because maybe he doesn't care about exactly 2. He care about 3, 2 or more, right? Then you have to calculate 2, 3, 4, 5, right? Care about add up this probability. Is it big enough? Then he will decide whether to replenish or not, so on and so forth. Right? Is that clear what we have right now? Okay. And you can imagine that many cases can be applied as well, right? Maybe the P is can be how likely that a machine is broken, right? And then probably you need to see how many spare machines have to be there, right? Suppose you are thinking about the subway, right? There's some probability that the train will fail, right? So you have to calculate how likely that there are more than multiple train fails, right? Then you have to engineer and thing to prepare. So that is super useful to calculate. Or just like a machine, you have a plane, right? A plane has many engines, right? And the plane will still fly if one engine fails, right? If the plane will die, I mean, not die, but the thing will fall down if more than 3 engine fails, suppose, right? Then in that case, we can do calculation, right? And then you can see how many engine you should need, right? It's an engineering problem over there. Okay, but of course, with B school, so we don't care too much about that. But this is the application. Okay, you can see that a lot of application over there. Okay, point out. So that's why I mentioned the example. Just we have seen if we have no more than 2, right? Why I care about this question is because we want to know whether he need to buy spicy from a restaurant, from other place, right, from the market, right? Because maybe in his restaurant he have 2 portion of the spicy, right? Then he don't need to buy if the P is very low, right? Just let it be, right? If more, then okay, people can just wait, right? But that would be the idea, right? Just add up the probability there, right? And this is actually the F function, right? F of 2, right? But don't worry, this thing actually Excel can calculate immediately without actually Excel have F function and P function. But for our case, we just keep it there. Okay. Now I think I have already talked about application, inventory management, quality control. You can look around and see how we've been that, right? And he see the marketing campaign, right? How many calls you have to make, right? To make successful, right? So that is going to be the scam park in Cambodia, right? This when you keep calling, scamming people, right? That is happening over there. But so this is the example. How many thing that will be make there, right? You have to do a lot of campaign and calculate the number, okay? And do the credit control, turnover. I'm not going to go into detail. There's a proof for the NP and the variance. I'm not going to explain why the formula here. I used to cover this during the first few years I'm in CHK, and then I covered this during the COVID time, but people hate it, obviously, especially in the COVID, they don't want to deal with the math. But I think even after COVID, you don't want to deal with the math, so I just skip. Okay, unless you really want me to go for the proof. But for those of you who want to do further in statistics, you should understand the proof. Okay, and the proof I think is very intuitive. I didn't skip any slide. You can easily look at it. Just have some patience with math. Okay, if you really don't understand, probably can just put my slides into the AI. The AI explain. Okay, I think that would be easier to see. But of course, you can always ask me or ask the TA for the help on this one. Is that okay? I hope I give you the idea why we need binomial. It's a lot of application. Okay, we can check those. But of course, I think in the exam or the assignment, I'll tell you what it is. Okay, but of course, in the real world, you decide which distribution should apply to your case. Okay? But for our assessment, I will tell you what. Okay. Now the next one we want to look is Poisson. Turn out this is very close to binomial, which you see, very close to binomial. Actually, it's based on binomial. Okay. What's that? Okay. Let me do it using a graph because that will be easier to understand. Okay. Now, what is the motivating question? Motivating question is the following. So suppose you are, I don't know, you own a restaurant. Okay, own a restaurant. Okay. This is you. Okay. And then the question would be, you are thinking about how many customers you can serve today. Okay. You ask it because when you start, you don't know how many, right? You ask how many today, right? So the question would be, how many today will be from 9 a.m. to 5 p.m. Okay. Right. This is a question. Okay. Maybe you're just monitoring how people come to your store, right? Then in that case, you have to care about the inventory in your store, right? So why this is related to binomial, right? You want to ask how many person, how many people will come, right? So why this is binomial, or And then why this end up in Poisson? So that's very simple. So let's make our life easier. Okay. Suppose this restaurant is not very popular, right? It's lucky they have one person in an hour. Okay, so this restaurant may be in the far deep inside in the forest. Okay, maybe very few people will come. Okay, imagine that you cut the timeline into every hour, right? So on and so forth, right? Every hour, okay, only at most one people will come or no. Okay, then how likely people will come in each hour is probability P, right? And each hour has the same probability, right? So from 9 to 5, how many hours? 8 hours. Right? 8 hours. 8 hours, right? So each one have probability P, people will come. Right? So that is what? That is binomial. Right? It's binomial with n equal to 5. Okay? P equal to P, right? Right? So maybe P is half, right? If you say half likely that people will come, right? Then that is a binomial that is n equal to 8, right? Suppose P equal to 1/2, right? So half of time that people come in, P equal to 1/2, right? So how many people will come? Then you can just, it's a binomial, right? Right? So it's a binomial, right? If only every hour has 0 or 1 people will come, right? Then they just, you have binomial, right? With n equal to 8 and P equal to 1/2. So that's simple. Now, the question probably you say, okay, this only apply to a restaurant deep inside a forest. Only if 1 people would come or no people come, right? And of course, you want to be a little bit more serious, right? Instead of cutting this, maybe you ask, okay, instead of saying, okay, let it make more busy, right? Not just every hour, maybe every half an hour. And most at 1 people will come, right? So then it become a n equal to 16, right? And P may be 1/4, right? Right, in that case. So and so forth, right? You can so on and cut and cut and cut, right? You can keep cutting. This interval time will be smaller and smaller and smaller and smaller. And to the so small, that become Poisson. So n is so small, then that is what we have. That is a Poisson. It's asking in a period of time, okay, and how many people might be coming, okay? It's not changing. It's proportional to the time period, right? Because as we see, right, every hour you have half of people would come, right? And every hour have likely that half people come, right? And every half an hour you have a quarter people would come, right? So that would be the idea. Okay, so let's see the formal definition, then you will see what's going on. So as I said, I divide the time interval into n time to n intervals. Okay, as I said, if 8 hours is 9 to 5, and each interval can be considered as a binomial trial. Okay, the trial, the period has success P and fail 1 minus P. Right? I mean, some people come in, it's success. If no people come in, it's fail. Right? Asking how many number of success, right? That's nothing different. So this is exactly the same as what we have seen, right? So this is the same formula. There's nothing new there. Okay. The only new thing is when n is very large, this formula can be simplified to the following. When n is large, P is very small. Okay. Turn out that we don't need to worry about the combination. Turn out to be this guy. I don't want to deal with the math, but this guy can be similar to this guy. Okay. I don't know whether you think it's simpler or not. In calculations, it's much easier. Okay. because combinatorics has 3 factorial, right? And here is only 1 factorial and exponential. So in terms of calculation, it's much easier, much faster. Okay. Of course, for computer, for our days, it's nothing different. But at least this will become this one when n is very large, p is very small. Okay. And what's this e? E is just the Euler constant, just a number there. Okay. It's raised to negative np, and np is x, and x factorial. So it's arrival of custom over time. Okay. And you may ask, okay, why we learn this? And turn out that if you learn advanced class of what we call stochastic process, using probability to model how things evolve over time, this Poisson is the baseline. So you go to that stochastic process in that department in 4,000 classes. The first lecture will teach you this. Okay. And then go on and go on, much more complicated. But this Poisson is the way that you try to model how things evolve. And the most important assumption is each one is independent, right? So here we have the formula. Instead of NP, we call it lambda. Okay? Lambda is what we call the rate, is how many people would come per unit of time. So lambda is the NP, right? And lambda is NP. Okay? Remember, NP is on average, how many people would come per unit of time. Okay? Because you use the time. And very interestingly, different from binomial. Remember, binomial is np times 1 minus p, and p is very small. So that's why the p is gone, right? So that's why we're np. That means lambda. So that's why in the Poisson, very interesting, is mean equal to variance, okay? Which is not, in general, it's not, right? But Poisson says so special, the mean equal to its variance, okay? And of course, this thing you have to know what they are, right? You have to apply, but we can always check from your slide, so we don't need to remember, but there's a calculation that we need to do, right? So let me do the calculation with a break, so don't worry about that. You want to visualize the P looks like. When lambda is small, it is more skewed to the right, but when lambda is large enough, then it looks like very like a bell. Okay, remember, this is still it's a binomial coming from, right? So that's why it's very similar to binomial. When lambda is big enough, then it's very close to the bell curve, which we will talk about bell curve probably next class, okay? After the National Day holiday, right? But that would be the idea. Okay, let me quickly go to the example and then we'll break. Okay. Again, this example is we have said, right? Every hour, people would come can be modeled as Poisson with mean 5. What does that mean? It means that every hour, on average, there are 5 people who come in, and variance are also 5. Okay, so that's important. So when you get the 5, how you get that from the data, right? Look, historical data, how many people will come, right? And on average, 5 people will come, and you check the variance of 5. In that case, you are safe to use Poisson, right? Look at data. If the mean and the variance are 5, then Poisson is a good fit. Okay. If that's not the case, you have to use other, but that will fit our application. Okay. You can use other if it doesn't fit your data. Okay. Now the question is, will probably exactly 2 people would arrive. There's nothing new there, right? Because you just put in a number, right? Put a number there, right? Because it's e to the negative lambda x factorial, right? So lambda is 5, x is 2. You put that in, you're done, right? And e is just in Excel is exp, right? Exp bracket and negative 5 and times 5 raised to the power of 2 and 2 factorial. Or maybe I just show you the Excel quickly, in case those of you who just very curious. Just bear with me one minute. We'll give you 15 minutes back, don't worry. Make sure that you're the full break, okay? Exponential, negative 5 raised by 5 raised to the power 2, right? X is 2. And factorial is fact 2. Okay? So this is the answer. And same as what I have shown you there. Okay? Of course, you can use the calculator there. Okay? You can use scientific calculator, you can calculate that. But this is why we have 0.8384. You see. Is that okay? Is that okay? But of course, don't worry too much about it because it's very unlikely that I will ask you in the exam direct calculation of something. It's not my purpose. But you will see it in the assignment, right? But I very unlikely to ask you to do something so simple, right? Asking you to do this in the exam, that will be too easy. It's open book. So you shouldn't worry too much about calculation because if I ask that easy, then everyone got a good grade, right? So I mean, of course, some questions very easy, but this is too easy, right? Because I ask you this, then you just get the solution in a no second, no time. So okay. So if that's okay, we'll break of 15 minutes. We'll resume 15 minutes later. At the meantime, I recommend you to try to do this for me to know your attendance, your participation, and I know how well you are understanding about this, whether I need to speed up or slow down. Thanks a lot. I will see you 15 minutes later. It will be 3:35. I was about to speak. I didn't even know that. So let's get back. See if you have any question, suggestion, and the things. I want assignment one answer now. Yeah, I think the TA will release after it's over, but it shouldn't be too difficult, right? I guess there's something called AI, right? Although you are not allowed to use it, but who knows what, right? But please use your brain to process it, right? Even though there are answers, because it's very hard to avoid AI, because now the Google, you ask it, it immediately gives the AI an answer. So it's very hard not to use AI these days, but you can try to see if AI help you something. But as I said, try not to. When is midterm? Midterm will be at the infinity because we don't have midterm, so no midterm for this class. So no midterm. So I don't know why you asked, but there's no midterm for this class. There are quizzes, but quizzes is just by attempt. So as long as do it, at the end of the day, then you get the credit for that. Because some people really want, because no midterm, some people say, I want exercise. Okay, I satisfy you. I give you the question and answer. You can just work it as many as you want. Okay. If you really want more, I can try to create more, but I guess it's enough. If not, then you can just go to the textbook. There are many questions already there. Because our class is very generic class. So whenever you pick up the thing, you try to pick up a textbook with answer at the back, then do those. And also these days, AI is very convenient. So you can just, later you see my answer, my question, you can feed to the AI, ask them to generate something similar. Then they can do it, right? I mean, you can't use AI for generate the assignment answer, but you can ask them to generate something similar and learn how to do that, right? I think that is the thing that is so good for you guys. It doesn't exist in my time, but you guys are very lucky. But I feel like when at my time, I try to find exercise very difficult. Now it's very simple. Okay. And let's see the next question. Just remind you, no midterm. We only have one final at the very end of the semester, right? I think the final will be the November 28th. Okay, 1 hour. Okay, just only one final. Just to make sure that you see, I mean, in case you don't, just look at the course outline again, because we want to make sure that everyone in the same place. So our assessment only have the final exam, your projects, your quizzes and problem set, which are already there, and the participation is a U reply. That's it. There's no midterm, so don't worry about midterm. There's no midterm. That's why I never thought about midterm. Okay, so there's only one final, one group project. You have done. There's no this one. For me, I don't have this one. This group project. Only the final and the quiz and problem set there, and then we have done in the class already. Okay. So in any case, yes, not Friday yet. It's not that there. Okay. It's very hot today. Surprising. Understand the meaning of Bernoulli? Yes, that's true. P(x=2). So you learn hard. Okay, that's good. Learning love is very important in Christianity, right? The central meaning of Christianity is love. Hopefully, you got that part. Probability, loss of visibility. Yeah, that's true. Yeah, that's good. The speed is okay, so I'm happy that happened. Most of you can follow, and I'm guess it's the same same thing, all right? Is it going to be the same trick? Let's see.
就算这次做错也只是把我爱情长哦，漫长哦，是不是说没有做完的梦最多？谁敢
Okay, we have. I don't. Maybe that's fun. Nice haircut. Oh yeah. Thanks. It's a blue heart. What does the mean blue heart? Is it going to be sad? Not sure. Is it blue and red different meaning or same meaning? I don't get. If you want how to do homework, ask TA. TA is the one who has all the homework because she'll be grading all the thing. So that would be you should ask her. But I guess the homework you should able to find anything from lecture slides. It's not. There's nothing new there. It's not. I'm not asking any creative assignment. It's just applying what we have learned directly. So if you have question, basically everything on the slide. But if you really, really don't know, try to ask help from AI. Sorry, to TA. The TA will not tell you exactly how to do, but probably may point to you which slide you can look at, and that would be we can help you on this one, but not telling you the answer, right? But she tells you probably you can look at which slide, which page you can check it out. I think that would be a fair help. Okay. So just before the break, we talk about the very important two cases, which is binomial and Poisson application, right? You can see the Poisson is super useful because we often ask over a period of time, how many things would happen, right? In modeling a lot of scenario, and dynamics and Poisson is something that is super useful thing. Okay. Like this, right? Look at the call center, how many calls you would have, right? Website traffic, right? How many customer would do it, right? And then you have to prepare for the spike, right? And manufacturer defect, right? And then service downtime and then insurance claim. How many claims will we make, right? Over the period of time, right? These are all the example. You can see how this thing can be applied. Of course, this probability modeling is beyond the scope of a class, right? We're not asking you to give a situation, how you model it, no, right? We'll just give you directly what it is, just apply the formula there. But you can see this thing can be applied, that's why it's technical. So this for you to read, you can have a fun, but if you don't bother, that's okay, because this beyond our class. But telling you that why we have to learn probability for which required for all of you, because it is applied to everything you will learn in B school, right? Because when we talk about uncertainty, you have probability. When we talk about future, it's uncertain. So that's why business is about make decision for the future, right? So you always have this. So there's no way to avoid probability, no way to avoid probability modeling. You always have this, right? So I hope that I convince you why we have to study all this, right? And if the future or the past is dependent on yes or no, what's happening or not, then you have binomial, right? A number of people who come in is Poisson. So you always have that, right? You can't have how many people come, how much success you have, right? And that is very natural to see this one. So how many visitors will come to the traffic? I'm not going to go into detail. I think my slides already clear enough to go on. But if you still have a question, either ask me or ask the TA, or you can write down in your you reply. I can actually answer them. Okay, that's always I will try to answer things in the you reply. So we're next one. This one you will see closely related to auditing, inventory control, quality check. Okay, and this is closely with the binomial, but this is a little bit a more realistic version of binomial, you can say, or a different type of binomial. Okay, you will easily check. And this is a kind of dropping the independent assumption, right? Remember binomial, each one is independent draw, right? Every drawn is have same probability success is P, right? Poisson is every period things happen independent, right? Every hour, right? Telling you what happened this hour doesn't tell you the next one. So now hypergeometric is kind of dropping the assumption of independence. Okay, and this is very useful when you talk about the population is very small, right? It's smaller than what you think. So what's this? Consider the following. You have n items. Okay, it's how many people in the population. Out of them, A of them, okay, is belong to success, right? You can imagine that there's a 10 people or 10 in, maybe we'll use inventory as example. You in a warehouse, right? And there are maybe 10 items, okay? And out of which, say, 5 of them are good, okay? 5 of them are bad, right? Say, or maybe 5 of them good, 5 of them bad, right? So if 5 are good, 5 of them bad. And suppose you allow only to take 1 item, right? Check whether they are good or not, right? Because sometimes you quality control, you have to destroy it, right? Suppose you want to say, right, the client told you that there are 10 product, right, out of which 5 of them are defective. It's a food, right? So you not see the, say, the food is in the can, right? Then you have to open it, right? Once we destroy the product, right? A lot of time when you check the product, you have to destroy the product. So you can't actually open everything, right? If you open everything, then it's okay, but you really can't, right? So if you only take 1 item or, right, there's a small n, right? And because you take the item, it's without replacement. Because you take it out, you can't put it back. Because you take it out, you just destroy it. Or once you take it out, you remember what you take out, right? Then you're asking how many items are good items. This is X item or good number of good items, right? So this is saying that, again, it's a auditing thing, right? You may be go to warehouse with 1,000 product, right? 1,000 goods. And the client told you that 80% are good, right? So it means that out of 1,800 are good, right? And then probably you can't check everything, right? Because the checking actually destroy things or is costly to do. Maybe you take out 10 of them, right? 1,000, take out 10, right? The question is, out of 10 product you take out, okay, how many are good? Let me write down the graph because that will help you, because seems to be the first time you learn it, it's very confusing. If I were you, I'm confused as well, right? What I'm talking about, right? So this is the way we're looking at. You have n object here. 1, 2, maybe this, right? Maybe it's food, right? Maybe that's it. Item number 1, item number 2, up to item number n, right? This is food can, is can of food, right? So you have to, someone said, okay, our product is so good, say 99% of them is good. Okay, that is what they maybe claim, right? Suppose you have 1,000, this 1,000, right? There's 1,000 can over there, right? The claim is 99 of them are good. Okay, 99% of them means A equal to 990, right? Then this is claimed by the guy, right? You are the inspector, right? You want to see whether this is good or not, right? Because it's a food production, right? You are the government, you want to see whether they're good. Or auditor, you want to check whether the claim is all right, right? And that means that you have food, right? And 990 is good, right? And then if you eat this, then you will die, right? 10 of them is bad, right? So the question is, now you can't check every single one. If you check, then basically open all the food, then basically the store will go bankrupt, right? So what we're going to do, right? Not going to do everything, right? Maybe just take out 10, and it's 10, right? And it's 10. Take out 10 of them, right? So you take out 10 of them. There are 10 of them, right? 10 of them. The question is, out of 10, how many of them is good or bad? So the random variable is 10, right? The outcome is either 0 up to 10, right? Because 0 is good, 1 is good, up to 10 is good. Okay, so that's a question, right? We want to see how likely that is good or bad. Okay, because that is what you expect, right? Because someone told you this is the case, there's someone you can see, right? And why this with the audit or product control? Because it's related to what we learned. Some idea we will learn 3 weeks later. We call hypothesis testing. So, of course, in the real world application, you know the back end. Okay, A is claimed by your client or claimed by the guy, the firm, manufacturer. You're the inspector or the auditor, right? You can't see A, right? But you can observe, you can do N, you can observe what actually happened, right? It's reverse what we learned, right? Here is, I know A and N and N and low, this is the probability, right? But in the real world, it's reverse, you know this guy, but you try to get whether A is true or not, okay? And what hypothesis testing is like, you claim the A, and what I observe have very low probability, then I challenge the claim. That's it. That's what we do in the 3 weeks later. That's how you reverse the ordering, right? Under your claim A, right? Suppose you say A is very large, right? Then the probability having, say, 5 of them are detective is very low, right? Then, but I have 5, then I think the A you said can't be right, right? That's the idea. But you talk about this hypothesis testing 3 weeks later, don't worry about that. At the moment, you just say, we know what happened in the world, this is N, this is A, and then what happened? Okay. But when you use it in practice, you reverse it. Okay. And this is actually what we call sampling without replacement, right? We're just asking people to come in and ask, right? Because I said, right? Suppose in the world with 1,000 people, right? 990 people like a particular pop star, right? If you ask individual, okay, and we just usually is get them without replacement, right? We meet the people. If I saw him, I don't ask him again, right? In that case, this is the appropriate one. If I ask him, I ask him again, there's a binomial, right? Because every time I pick up a person, I put it back and I may able to draw him again, it's okay, right? When N is very big, then it doesn't really matter, right? No matter, it doesn't really matter this assumption. So when that basically, the binomial and the hypergeometric will be very similar when the big N is super large. Big and super large doesn't really matter whether you put the same guy back, because there's no way you can draw the same guy. Okay. So this is why this is called sampling without replacement idea. Okay. But again, don't worry about the application. For the moment, you just need to know the formula. It's not something complicated. Okay. It's just combinatorics. The denominator is N, Cn. Why? You have big N, you draw N. That's how many things you can draw, right? It doesn't really matter, right? Because that is how many outcomes you can draw. And why is this? AX, because this is good. X outcome is good, right? Out of A, you can draw X. Okay? Out of N minus A, you draw N minus X. So maybe make it easier to think. Why this is the case? You have number of can from 1 to 1,000, right? How many likely you only draw 10, right? So that means that you have balls 1,000, how many ways you can draw, right? That is 1,010, right? That's how many ways you can draw it, right? Imagine a ball 1 to 1,000, how many you can draw? Why you do C? Because you don't care about order, right? 1, 2, 3, same as 3, 2, 1 or 2, 1, 3, right? And suppose how likely that 3 of them is good, right? So you have 9, 9, 0, which is good. You draw 3 of them is good, right? And out of 10 that's bad, you want to draw 7 of them, right? So that would be the probability that out of 10 things you draw, okay, 3 of them is actually good, 7 is bad. Is that okay? Because that is how this is a why multiply. This is principle of counting, right? It's how many ways out of the good you draw 3. Right? This how many ways you can draw out of 10 bad, you draw 7. Right? The bottom doesn't really matter how you draw, right? Because how many different ways you draw it. It doesn't care about good or bad, right? Out of 1,000, you draw 10 of them, right? The balls are, you have the 1,000 ball, you draw 10 of them. How many ways you can draw it? Is that okay? Of course, as I said, you don't really worry too much if you don't get the math, but because I'm not asking you to do the math, but I hope try to make sense this. Okay. And this is the formula we have. Okay, just saw it. And this is what? This is just n times a over n. Okay, a over n when was just p. If you just draw once, right? If you just draw one guy, the probability that that guy is actually belong to the good item is a over n. Okay? But turn out to be this also hold true if you draw n different objects. It's just n times p. Okay. Of course, it's coincidence, but turn out to be doesn't really matter. We draw things without replacement, okay, and draw things with replacement. The expected number of success still the same. But the variance turn out to be super complicated. Okay. But if you remember, this is actually p, right? And if you look carefully, this is 1 minus p, right? It's n/p minus p. It's actually variance of binomial. But now, because of your finite number of samples, so that's why you have this guy. And if n go to infinity, this is just 1. Right? Where big N is very large, this is 1. So people call this is, sometimes in statistics, this is called finite sample correction. I'm not going to talk about I'm not talking about terminology, but it's basically because of, that's why when n is very large, binomial and hypergeometric the same. So that's why we learn binomial. Because binomial is the thing that is easiest to see, right? But when you have small sample, when you audit, that's what we need. Okay, because that's what we see. Okay, so let you see the example, and then hopefully that will convince you why we have this kind of thing, and it's very useful. Okay, so I have to talk about this idea, finite sample adjustment. Okay, so the shape is, as you see, is very similar to the binomial, but let's see the example. Okay, I think that is the thing that you do auditing. There's a problem there. Okay, so now the warehouse people claim there are 30 computers, out of them 4 are defective. Okay? And what is the probability that 2 of them are defective out of the 6 samples you draw? Okay, so just repeat the question. The warehouse have 30 computers. 4 of them defective means 20. We want defective. 4 of them are bad. 26 is good. Okay, but now bad is the thing we care, right? Bad is a success, right? Remember, no, bad is success. So we are them 2 of them out of this. So basically, look, this is n, okay, and this is a, okay, and this is small n, 6. This is x is 2, right? And 6. Big N is 30. Big A is 4. Right? So that's a question. Then just plug it in, then that's the answer. Right? Because 30 computer, right? You just name 1 to 30. How many things in draw? 30 over C, right? 30C is 6. Okay? And you 2 of them success. You only have 4 items. You have to draw 2 of them, right? So 4C2. And how many is good? 26. And you have to draw 4 of them, right? Because you pick 6. So that's probability over there. Okay. So this is the probability 0.15, okay, 15%. Okay. So there's not a small number, right? Interestingly, right? Even though majority of them are good, right? And you will see 2 out of 6, 1/3 of time is bad. It's still not non-trivial. Okay. Right? Because okay, so that is the answer. Okay, there's a lot of idea, right? Because you have to do the inventory control or hiring or management. But basically, just like you can think of same as binomial, but we have some small sample there, right? If small sample there, basically just like that, right? Basically, you can say Poisson is a case where n is very large. Hypergeometric is n is small. And the baseline is binomial, right? Baseline binomial when n is very large, then go to Poisson. N is small, then you go to hypergeometric. So that's why we cover that. That's why you look at the textbook, they covered 3 cases. The baseline will be the binomial. Okay. And that happened for you to calculate those. Okay, I think that's already there. I have example over there. I'm not going to go over one by one because I don't think it's worth the class time to go over this because you will be doing assignment on those. Okay, because I asked you to do some exercise like the example. I remind you that you should try to look at the assignment again, example again, when you do the assignment, because that will be very similar. And luckily, when I give you assignment, I'll tell you what it is in the question. So you don't have to worry about, in this question, what exactly distribution I should apply. I'll give you directly, okay? But do note that when you actually go out to work, okay, you have to figure out what it is. Of course, your boss might usually tell you, but if the boss doesn't tell you, you have to figure out which one should fit your case, okay? Is that okay so far? Okay, we're faster than we do very happily, so we can go to the continuous. So because we're at bonus time, so we don't have to go too fast. It's a bonus time now because you don't have question. So good. So continuous random variable. So discrete so far we have said is 1, 2, 3, 4, 5 is a number, right? It's a counting number. We have counting number of success, right? It's an integer, right? So I mean, in describing our future business decision, a lot of times it's not in 1, 2, 3, 4, 5, but rather actual decimal numbers, right? Price of the stock, right? How much money we make, right? Those kind of question is not really discrete, it's continuous, okay? But when it continuous, there's a lot of problem because the P function is not defined. Okay, in general case, P is not well defined because it can be any number. A particular number you give me will be basically 0. Okay, so we can't use the P function, but luckily the F function is still well defined. Okay, so why? Because why is not the case? Because if a particular P have some number is not 0, okay, because say suppose your random variable is from 0 to 1, okay, number from 0 to 1, okay. If say 0.5, you put a probability there, okay. 0.4 put some probability, okay, and then remember any number between 0.4 and 0.3 with some number there, right? And if you put some number in any number, you add up because many infinite number of them, you will blow up more than 1, right? Because there as many as you want number between 0.3 and 0.5, right? So it just cannot have any number. So you can only use the cumulative one. So this example, let me start with this example we know very well. So we have P function and F function, right? Put the coin once, right? This is the function we know very well. If you stack the left-hand side, you get the right-hand side, right? If unstack, go to the other way, right? So this is, we know very well already, just recall. And this is the case if you do it 2 times, put the coin 2 times, right? You have, it's uniform, right? This uniform is a free-size coin. You have 0, 1, or 2, equally likely, right? Just imagine the coin have 3 sides, but I don't know how to imagine, but you imagine there's something come out 3 outcomes, okay? And if you stack this together, it's like this, right? 0 is this one, and 1 is 0 next to 1, and 2 will be just stacking everything before it, right? Now consider the case you have more than 1 uniform case, okay? You can keep going, and going, right? And do note what happened. What's the height of this? The height of this is 1 over n, right? But if n go to as many as you want, this becomes 0. This is still well defined. It looks like it's a upper sloping line, right? When you go n, the first one is 1 over n, this is 2 over n, and so on and so forth. Right? You still have a 45-degree line, this one. But for this one, everything collapsed to 0. That's why f is still well defined, but the p, everything is 0. Then what I say? Nothing we can say, right? Right? Because say suppose this uniform 0 up to 1,000, say, right? Then this become 1 over 1,000 is very small, right? But this is look like the first one is 1 over 1,000, second is 2 over 1,000, so on and so forth. Right? So you can still say something for the f, the big F. But the p, everything is so small at the end, it's meaningless. Okay. So that's why, and there's so many, it's not very useful anyway. Okay. So that's why the motivating of this example tells you that you don't want to talk about the p. So don't talk about p, right? So we will start from f. This is the same as the discrete, nothing new. No new definition. Same definition. Okay. But now we would do the following. Okay. We would, because of f is like less than or equal to, so we have this same idea. Okay, which is also true in the discrete as well, but probably x, the random variable between b and a will be fb minus fa. So this is, we have that already in the discrete. There's nothing new there. Do note that there's no equality sign here, right? Because it's equal, less than or equal to, right? It's already included in a. And then f bigger than b is 1 minus fb. So this is, we have that already from our discrete. Okay, so there's nothing new there, right? And the question is, we like the p is very intuitive. Okay, then can we have something like p in continuous? Yes, we do. That is called the probability density function. What's that? If you learn physics, there's a mass, but you add up the density, is the mass. You differentiate the mass, is density. Okay, if you learn physics. So that's why they call the probability distribution function or probability density function. Sometimes they call. And what's that? Actually related to integration and the idea of the idea of that. Okay. But what's this? This is the following. We've seen this very often. So we will have a function called f, okay, that captures the idea of probability in area idea. Okay. If I want the probability less than a, will be the size of this area. And the value of this size area will be same as f of a. Okay. If you learn calculus, that's integration. So you integrate over the small f, gives you the big F. If you learn the calculus, you differentiate the big F, give the small f. So that's why you say small f and big F if you learn calculus. If you learn calculus, it's okay. You just need to know area. Area under the small f gives a big F. Okay. So basically, the big F is the area function for the small f. Okay. If you don't want calculus. Okay, that is what it is. And if you want to know the probability bigger than a, will be the area in the curve bigger than a. So this area will be 1 minus fa. Okay. So that means that the area under this small f curve must be 1. Let me repeat. The area under the small f curve must be 1. Why? Because probability of the sample space is 1. That's axiom 3. So 2. Right? So it must be 1. And if you want the area between A and B, will be just the area between that will be FB minus FA. Okay? And in particular, the probability of particular value is 0, so it doesn't really matter. So that is the idea. That's why I write down here. The probability between A and B will be the area under F from A to B. Okay? Okay? That is the calculus idea. Okay? but we don't use calculus, so just we define directly the area under F, A, and A to B, okay? And how it exists, if you learn math, this is the idea. The property, this is the differentiation idea. Just change a little bit and divide it by that, that's density idea. So I don't want to talk about this because there's involved calculus. Okay, if you know, you know. You don't know, forget about it. Doesn't really matter because unless you really do calculus, you don't really need it. Okay, I think in B school, no one need it. Okay, if you go to stat department, you will have need it. Okay, so since I guess none of you can do the stat department, so just safely skip it. You can see it's on the gray area. Okay, but that's why it's called. That's why I said F is probability for intervals. You give me interval, F the area will give you the probability. So because you can't define probability at a point, you can't probability interval. Okay. And that's the calculus using the ideal limit, the calculus, that's why integral and differentiation. So as I said, I don't want to talk about calculus. If you think this is a monster, leave the monster away, right? Don't worry, Superman, Ultraman, whatever man will come to save you, right? So you don't have to worry about this monster, right? Just leave it there, right? Then you just happy with that. If you want to know, then just forget about it, okay? And I don't want to talk about the math there, okay? Just a gentle reminder is because probability of each point is 0. So that means that these last 4 statements are all the same. Okay? There's no ask me particular point would arise, is 0. Okay, so that's very important. Because if you don't know, then you will get confused. So another thing I want to talk about, maybe I just talk about this and then we call it today. So remember the F function is like this, right? F is from, you draw somewhere, I don't know, somewhere start from 0 and then go up, blah, 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 blah. But remember, always at most is 1, right? You cannot more than 1, right? Because this probability, right? At most is 1, right? And this must be increasing, right? Because you cannot go down, right? Because it's, and what I said here is there's x here, some value. You go up, you get to this value of y, right? So this y is f of x. But if you learn math, if you can, because it's 1 to 1 increasing, there is called inverse of f. You give me the y, I give you x. So for every x, I give you a y. The inverse is I give you y, I give you x. That's called the inverse. I give you some value on the vertical axis, I give you the value of y. That's called the inverse. Okay, and this will be very useful. Later you will see when we talk about bell curve. Okay, because from number I give you probability. If from probability I give number, is the inverse. Okay, which we soon will use it. Don't worry, we'll use it for the rest of semester for this inverse. So don't worry about that. So, but let's talk about this in the big now because I don't want to rush because it's already time is over. So, but this is called the inverse. So make sure that you get inverse of f. Okay. So inverse of f is you give me this, give a probability. I'll give you the value that's such that this number is probability, the whenever we equal the net to that number is that probability. Okay. To repeat before you go, f is you give me the value of the probability, which is the value of the random variable, right? Then I will give you the probability that the random variable less than equal. And you can reverse it, right? I give the probability. I tell you the number of the random variable that the random variable less than that or equal to that. Anyway, we'll talk about this next class. So enjoy your national holiday. Have fun. I see you on Wednesday, well, Thursday.